Speaker is from all the way down under. I'm not sure whether you're there or in MIT right now, but he is distinguished professor Saeid Nahavandi and is from Swinburne University of Technology's inaugural Associate Deputy Vice Chancellor Research and Chief of Defense Innovation. And he actually previously served as Pro Vice Chancellor Defense Technologies and founding director of the Institute for Intelligent Systems Research and Innovation, Deacon's University. And Syed received a PhD from Durham University in UK, 1991. His research interests are autonomous systems, modeling of complex systems, robotics, and haptics. He has published over 1,300 scientific papers and various international conferences and journals. And Saeed has carried out industry-based research with several major international companies such as Airbus, Boeing, Bosch, Ford Company, General Motors, Lockheed, Nissan, and others. And he holds 6 patents, 2 of which have resulted in 2 very successful startups. And he is chair of Assembly, Australian Academy of Technological Science and Engineering, and current Vice President, Human Machine Systems in SMC Society, IEEE, Senior Associate Editor for IEEE Systems Journal, Associate Editor of IEEE Transactions on Cybernetics, and IEEE Press Editorial Board Member. And he is a Fellow of IEEE, Engineers Australia, the Institute of Engineering and Technology, and Saeed is Fellow of Australian Academy of Technology and Engineering. And he actually was the General Chair of our IEEE SMC 2021. Saeed, floor is yours.
Thank you very much. Good morning, everyone. And it was what a great pleasure to listen to Alison's keynote speech. So I was online listening. And my talk is going to be around a series of systems that over the year myself and my research students we have developed. And some of them, they are around robotics, big robots, and how we enable large robots to become haptically enabled, and in particular simulator, and some of it around medical simulation. So let me take you through the journey. So around 2006, there were large robots that they were notion of that turning those robots into theme park ride kind of activities. And I start thinking that can we use those robots as a motion simulator so we can simulate certain type of activities such as driving, flying, and so on, but at the same time to be haptically enabled. And so quickly I went and developed a concept system and then patented the technology and then applied for the Australian Research Council. And I was lucky enough that I received a few grants to enable me to purchase the system and demonstrate as a proof of concept and then take it to industry. So that was the journey. So purchased the robot, as you can see on the screen, and then developed end effector. End effector in this case is a seat. And then, so here we are talking around 2008, 2009 technology, head-mounted 3D head-mounted display, and then had to develop a haptic steering wheel, and also for aircraft type or helicopter type activities, a haptically enabled collective and cyclic for helicopters. And so to do that, or to go in that journey, so we had to actually design the gondola, then develop vehicle dynamics model, and then look at the simulation, environment integration, terrain generation, motion tracking, and motion cueing algorithm, and to make sure that what the driver or pilot see and what they feel and experience, they are in sync. Because as you already know, that if they are slightly out of sync, the person get motion sickness, and most probably they never ever go inside that simulator again. Um, so at that time, I was looking at, I knew that there were a lot of motion platform, golf platform simulators. There were a giant company, CAE Systems, Thales, and so on, and were selling their simulators. So I didn't want to compete with anyone, and all I wanted to do to see that whether we can create a new class of motion simulators, but at the same time, they are haptically enabled. But while in that journey, I actually proved that with a robot like the one you see on the right-hand side of the screen, with a work envelope of 13 meters in diameter, and in terms of reach of 6 meters, 6.5 meters, and also having two continuous uh, rotation on two axes, axis 4 and axis 6, we can provide the kind of motion fidelity no one else was offering then. So that was the journey where it began. And I just show you quickly that I hope you
Now,
can see
before we start, a viewer warning. If you're a high-tech junkie who gets jealous watching someone else enjoy the latest and greatest thrill ride, look away now. On the other hand, if you're about to jump into a military chopper, fighter aircraft, and go into battle, you've got to check out this. It's called the Universal Motion Simulator, or UMS, where a pilot is perched on a 7-meter long robotic arm, capable of exerting up to 6 Gs of force. That is impressive. The man at the controls of this next generation motion simulator is Professor Saeid Nahavandi.
So let me move on, because I don't want to play all of the videos. So when it was the simulating a Black Hawk helicopter and showing that the kind of the range of motion we can create, it is far greater than all of the existing motion platform. And this will allow the vehicle air platform or land platform manufacturers to test their system, to do the edge cases, to do all those kind of tests for edge cases. And then later on, the platform has become a system where vehicle manufacturers, they have used it to actually do rapid prototyping of their platforms. By the way, the video you saw, it was in one of my laboratories, and actually getting university lab and then putting a system like this is another story. Another day I will tell you how I went about that. But the other thing was that until then, having a person inside the robot and getting the person in real time, controlling the motion of the robot, and at the same time doing it safely, was a huge task that I had to have several engineers to double check, triple check all aspects of safety to ensure that we can make it safe for human use. So that was a big task. It wasn't just proof of concept to actually make the system actually human ready, and obviously not to hurt any human. And we have never ever had any accident, and that system has been commercialized and sold many. Another application is where, in this case, person driving. So it became from an air platform simulator into a land platform simulator. And we had interest in various military vehicles. So we started with very old military vehicles to learn how we could actually bring the information sensation of the motion to the driver so they can actually feel it. So the fuel shift was happening and then pedals would feel realistic and the way you brake, the acceleration, deceleration, all of it would look realistic. In terms of creating, as I said, motion cueing algorithm and providing the right level of sensation to the human user all the time was our biggest challenge. We had to use various tricks like voice coil. We had to build it inside the seat to create certain frequency of vibration. So the person actually feeling, if it was a big military vehicle, diesel engine and so on, that they're actually sitting on top of the vehicle, on top of the engine, and actually it is a real engine rather than just a simulator. And later on, I will show you maybe in a couple of slides from now that we in fact messed around even with the smell as well. This particular slide you see, then we wanted to validate this haptically enabled robot with the real vehicle. And so a real vehicle top left of the screen is a robotic, there is a steering robot, and you sort of program the vehicle for a certain motion, and then it exhibit that motion. And these are on the proving ground of major auto manufacturers in the world. And then we sensorize the vehicle, we put everything on the vehicle, and then we sensorized our robot platform, and then we created the same and played back the same motion to ensure that when the person sitting inside the simulator feels exactly the same motion as if they were testing that vehicle inside the test track. And so top left, you see the person inside the vehicle. Top right, the person is watching. Bottom two pictures is actually inside the lab that is connected to motion that the person feels exactly as if the person was sitting inside the rear view. I see the way it comes to stop, that actually is the kind the person actually that so the person can feel that motion. Now then we could actually take it, being a robot, at a much higher speed and acceleration and deceleration to actuate or to control the robot path to create whether the vehicle has hit a curve or there is a side-on crash or head-on crash, but safely inside the simulator. Now, later on, after taking to auto manufacturers, I took it to Department of Defense and then created a M1A1 tank simulator. And that's where you see that the cockpit is slightly different. Produced the entire replica of actual vehicle with all of the controls of the actual vehicle, and then brought many subject matter experts, and then they sat in it, and then they actually helped us how to fine-tune the motion for certain behaviors of the vehicle. For example, if he's going at the top of a hill and it is a knife edge, and how the whole vehicle, say 50-ton vehicle, should behave when you are at the knife edge and then you are descending, or if you're ascending, or if you're going at 80 kilometers an hour or 100 kilometers an hour, with 55 tons vehicle kind of thing. Now here we learned that maybe as we are doing this, we were asked that everything is great, but it doesn't smell the same. So actually we put a little bit of dirty oil rag and a little bit of diesel and those kind of thing, rubbing it around the seat and so on, to create that kind of sensation the person actually really is sitting inside the inside the vehicle. And in fact, even the lighting system, the sound system, we recorded a lot of sound and got sound bite that as you are accelerating, decelerating inside the simulator, you exactly hear the way the sound of the engine on the particular platform was. And again, that one, after being successful, they set up a company startup, and that startup employing around 60 or 70 people, and has secured a large sum of contracts. And while that was happening, they moved on to another concept, that to get again, instead of the previous robot you saw that could carry 560 kg, to carry 1 ton, because we wanted to do bigger thing. Then modified the robot and put it on a 12-meter long skid or linear drive. So this is direct drive linear electric motors, and then put all of the controller at the back of the robot, at the base of the robot, with lots of slip rings, and then the base of the robot can rotate 360 degrees, and then axis 4 300, infinite rotation. So base is infinite rotation, in fact, and then axis 4 infinite rotation and axis 6 infinite rotation, while you propel it forward and back motion on this linear track. So this was to create the kind of motion, for example, a aircraft such as F-35 demands, and to mimic upset training for that class of vehicle. So as you already know, upset training is a kind of training that they actually train fighter pilots, but it is on a high G during certain rotations and so on. And a lot of pilots, when they go through their upset training, they fail their tests, and that's why some of them they become Air Force pilot, and some of them they become different types of pilots. Now, after that, they I was asked several times that these robots, they are great, so we can create high high amplitude but low frequency of vibration in terms of modeling and simulating corrugated type road condition. Can you create a different type of robot that it actually can give that kind of real sensation? So we can use the platform to prototype vehicle and fine-tune and do all of the vehicle dynamic modeling, and then fine-tune vehicles before building the first prototype. So this one, I worked with a British company and designed and built a 8 degrees of freedom motion simulator. This time it is a Stewart platform type, but it sits on X and Y axes as well, and exerts around 3.5 G of acceleration. And this one, again, I designed the cockpit both for passenger vehicles, but also for big vehicle like 50-ton, 60-ton vehicles, where the behavior of the motion and is very different from a small vehicle. And so what you see here, this is a big truck, and created a area of simulation. Well, we scanned the area where we wanted to actually create the model, and this is a test track. And as you can see here, it goes down a very steep inclination, and then going down here in this gradient, and being able to control 50 ton, and then brake and then reverse and so on is a challenging task. So had to make sure that not only the person visually see, but actually feeling that it is going downhill and the vehicle is accelerating. And then, as you know, with the big vehicle, as it accelerates, it jumps, gears, and goes into higher gear, and so on. So gear management was important, engine management was important. And here what I'm showing that actually nobody had done this before during their trials and testing. So I proved that using simulator, I can reverse it now. So those side mirror really just their computer screen. And so the images there split that you can see from on the side screen, side mirror, but it is computer screen, and reversing. And here we prove that not only you can use the platform, these robots, that it can give you the real motion sensation, you can also use it for driver's training. And some of the young people, when they join military, sometimes they might not, in fact, even have a driver's license. And then when they are demanded to go and drive big rigs, it is safer actually to put them inside these kind of simulator so they become confident. And again, this one got commercialized. Now let me move on. Hopefully somebody will tell me how many more minutes I have, then I can stop on time. Some of the other projects we looked at, it was during some wars and so on in the world. We were asked if we can create teleoperation of a robot, to deploy a robot remotely, but be able to remotely touch and feel and see in 3D, and then to diffuse IED or detect anti-personnel mine and diffuse it. So bottom left, as you can see, they are commercial device, but what sits as a where your index finger and thumb is inserted is our own haptic device. So two haptic device integrated into one. Bottom right, it was a portable system where we actually put the whole thing. And again, that is a commercial haptic device, but our own 2 degrees of freedom on top of that haptic device. But top left is we ended up designing and building a 5 degrees of freedom robot, the haptic device from scratch ourselves to satisfy the need of our customers. So we were in the business of designing and developing haptic devices. We always would buy as much as we could and retrofit it, but the kind of range of motion and things we needed and had to be battery operated, to be reliable, to be field deployed, and so on, challenged us. So we had to actually develop ourselves. So we actually developed these haptic devices, as you can see on the bottom of the screen, bottom left, and then the person sitting on a PMV, personal mobility vehicle, is like a mobile bunker. And then the robot, this is again, we developed several of these robots with the robotic arm, with the force feedback, haptically enabled independent digit control, so we could get the forces of left digit and right digit, bring it all the way to the person user's hand, and then they could do their work. So here you see again a lot of this work, that the reason I can report because older technology, but at the time they were really state of the art, that haptically enabled teleoperative system would work from a half a kilometer away, and everything was talked about latency and so on at the time was a big challenge, and how could we actually so here it is independent digit control. So we could put brush we could put hook, we could put gripper, we could put cutters and so on. And this is the actual haptic device with 3D. And here it is a nasty device that and then these are all the same color. We wanted to actually see if operator can lift it and put it in ascending weight order or descending weight order, and if they want to release it and grasp it and so on. So these were some of, and by the way, the base of the robot is a PackBot, and then the top is our arm. So we actually proved that our arm can be integrated to existing robots without any haptically enabled teleoperative capabilities. And here the person seeing in 3D, and then which wire to cut, and obviously always is the red wire you cut. This is a joke. Okay, let me move on. Then we looked at similar technology, but this was sort of easier end of the activity. During COVID, we saw that, okay, there is a need to use an ultrasound, put it at the end of a robot, and then teleoperate it, but at the same time, when we are doing sonography, to know the angle of attack, the amount of adhesion force between the end of the ultrasound and the skin, and to get a good image. So as you can see here, a radiographer, so these were some of our early trials, that we have a patient and then radiographer is there teleoperating. In this case, then we start using commercially off-the-shelf robot as much as possible, and then again commercially off-the-shelf haptic device. But then all of the safety, 7 levels of safety we built, and then discomfort control system which the patient holds in their hand. Then they can disengage the robot from the controller, so it can go into drive. As you can see on the right hand, the patient is holding, I don't know if you can see, a remote button that it actually disengages if the person feels uncomfortable. Now, let me move on. And then we actually took it through clinical trial for over 12 months. And again, here we had to actually take it in a hospital setting to see whether clinicians, they are comfortable to use it, and if they don't see the patient, whether they are confident that everything works the way it is, and is the ultrasound giving them the right information, meaning that are they scanning the way they should be scanning. Then we noticed that, and we learned that nearly over 80% of sonographer, since they use the ultrasound probe 8 hours a day, and in a particular posture angle, constantly applying pressure, they get shoulder injuries. So then we realized maybe there is, in fact, a bigger market than teleoperation for over the long distance. It could be really short distance, but while the person using a haptic device, they are not applying the kind of forces they're supposed to be applying with their arm. And we can scale down, we can scale up the amount of force control, and the person can operate many, many hours without injuring themselves. So that was a finding. And Professor Farad, how many more minutes do I have? Just
You have about 5 minutes.
5 minutes, okay. So what then we looked at, again, I'm talking, all of you guys, you already know the, minimally invasive surgical systems and so on, the likes of Da Vinci robots. I've had Da Vinci robots. I've worked with surgeons that they have been using Da Vinci robots since 2004, 2005. But one thing that at the time Da Vinci robots lacked, it was providing force reflection and sensation onto the hand of the surgeon. And we all know that if we change the surgical gloves of a surgeon, immediately they complain that, you know, they feel a bit different. And here for years, they've been operating using only visual servoing without any force feedback. So I actually start looking at, so this work, I did it jointly with Harvard University, and to come up with a system, instead of designing and building our own robot arm, since here we didn't need to deploy it in a sort of battlefield and those kind of things, so we could use AC power. We did a battery and power was not an issue, so it can be less being mobile and to be based inside the operating theater and those kind of things. So, and then by that time, there were all of these UR5, UR10, and many robot companies. They actually promoted human-friendly robots, which was a blessing in disguise, because then we could really use their robots and worry about the pointy end of things. So what we did, we actually developed instruments to go at the end of these robots, but it actually give you force feedback at the tip, and then to use again off-the-shelf haptic devices, but then to retrofit those devices with our own haptic feedback. So that's what it was as part of this. And they worked very closely with several surgeons. So here is one of the very experienced surgeons in Australia. And by the way, I worked with surgeon at Cleveland Clinic as well, heart surgery unit there as well, and then getting their views and opinion about some of these technologies. So let me show you. We actually took the technology at one of the simulation conferences, exhibitions, and demonstrated the technology there, while the real surgeon operating or using a sheath heart. So that is not a real human heart, it is a sheath heart. So hopefully you will see.
We are seeing a screen, but and sound.
It's very soft.
I think it's a big file. Let me see if I can bring it up. Can you see
Okay,
now?
no, it's fine. Yes.
Okay. Let me. Okay, here. So we created this simulator for the robot and the real robot. We could make it partially real, partially simulator, and then if through haptics we could feel the simulated robot rather than real, or if they were a real robot, then we could feel real robot. And in real time, we could see the status of all of the joints, the sensor, and then. So it was a platform that we can both visualize frame control and also see the end effector, both real and virtual. So this is our own instrument we developed.
All can be adjusted.
It's sensorized, as you can see. So the base here, we are all force feedback. And the camera system. So he's actually, I don't know if you can hear it, he's saying that he can feel the tissue hardness, those kind of things. Right, let me move on. And that was my last slide, and over the years I've been lucky to receive some recognition, and with that I stop there, and thank you for your attention.
Thank you so much.